Electronic pressure measurement is a fundamental aspect of various industrial, scientific, and consumer applications. It involves the use of electronic devices to gauge and quantify the force exerted by a fluid, liquid, or gas on a surface area. This measurement ensures operational efficiency, safety, and accuracy across a spectrum of industries. Understanding electronic pressure measurement. Principle of operation. Electronic pressure measurement typically relies on the principle of converting pressure into an electrical signal. Various sensor technologies are employed for this purpose, including strain gauge, piezoelectric, capacitive, and resonant sensors. These sensors detect the pressure-induced mechanical deformations and translate them into electrical signals. Before examining the types of pressure sensors, it is useful to mention diaphragm pressure gauges and the corrugated diaphragms used in them. Diaphragm pressure gauges. Diaphragm pressure gauges are instruments used for measuring pressure in various industrial applications. These gauges rely on the deformation of a flexible diaphragm to measure the pressure exerted on it. The diaphragm, typically made of materials like stainless steel or elastomers, responds to pressure changes by flexing or moving. This movement is then translated into a mechanical reading displayed on the gauge. Working principle. The fundamental principle behind diaphragm pressure gauges involves the application of pressure to one side of the diaphragm. As pressure increases or decreases, the diaphragm flexes, causing a change in its shape. This deformation is then linked to a mechanical system within the gauge, often a set of levers or springs, which translates the diaphragm's movement into a pressure reading. It is this deformation or deviation that electronic sensors use to read the pressure. Corrugated diaphragms. Corrugated diaphragms refer to flexible membranes used in diverse engineering applications. These diaphragms are characterized by their corrugated or pleated structure, allowing for greater flexibility and sensitivity to pressure changes. Features. Flexibility. The corrugated design enables more extensive deformation, making them ideal for applications requiring sensitive pressure measurements. Resistance. Corrugated diaphragms are often constructed from materials like rubber, metal alloys, or composite materials, offering resistance to corrosion, temperature variations, and chemical exposure. Uniform stress distribution. The corrugated pattern helps distribute stress more evenly across the diaphragm, enhancing its durability. Types of electronic pressure sensors. Strain gauge sensors. These sensors use the resistance changes in a wire or foil subjected to strain due to pressure, converting it into an electrical signal. They're widely used in load cells and pressure transducers, offering excellent sensitivity and accuracy. These sensors excel in applications requiring precise pressure measurements, such as aerospace, automotive, and material testing. Piezoelectric sensors. They generate electrical charges when subjected to mechanical stress, allowing the measurement of pressure. Their rapid response time and ability to measure dynamic pressure changes make them suitable for impact measurements, vibration analysis, and shockwave monitoring in industries like defense, automotive crash testing, and biomedical research. Capacitive sensors. These measure pressure by detecting changes in capacitance resulting from the deflection of a diaphragm under pressure. Capacitive sensors are ideal for applications requiring high accuracy and stability, like barometric pressure measurement in weather stations, altitude sensing in aircraft, and industrial process control. As an alternative to capacitive sensors, the displacement of a diaphragm can be measured magnetically by means of changes in inductance, reluctance, LVDT, Hall effect, or by eddy current principle. Resonant sensors. Detect pressure-induced changes in resonant frequency, providing accurate and stable pressure measurements. They find utility in high-precision applications such as gas chromatography, where precise pressure control is essential for accurate analysis. Fiber optical sensors. Fiber optic pressure sensors are a subset of optical sensors designed to measure pressure variations utilizing the principles of optical interference or changes in the properties of optical fiber under pressure. These sensors are used in various industries, including aerospace, automotive, medical, and industrial applications, due to their high sensitivity, immunity to electromagnetic interference, and ability to operate in harsh environments. Fabry-Perot, Sensing Interferometer. The Fabry-Perot interferometer is a fundamental design employed in fiber optic pressure sensors. It consists of two parallel reflective surfaces separated by a cavity, typically an air gap or a diaphragm. When pressure is exerted on the diaphragm, causing deformation, the distance between the reflective surfaces changes, altering the interference pattern of light traveling through the cavity. This change in interference pattern is then correlated to the applied pressure. The Fabry-Perot sensor's key advantage lies in its high sensitivity to minute pressure changes. However, its design complexity and susceptibility to temperature variations may require compensation mechanisms to ensure accurate pressure readings. Fiber Bragg Grating Sensors. Fiber Bragg grating, FBG sensors are another prominent type of fiber optic pressure sensor. These sensors consist of a segment of optical fiber where periodic microscopic alterations in the refractive index are induced along its length. When pressure is applied, the grating structure experiences mechanical deformation, resulting in a change in the grating period and subsequently altering the reflected wavelengths. This alteration in wavelengths is used to measure the applied pressure. FBG sensors offer advantages such as immunity to electromagnetic interference, compact size, and high sensitivity. They find applications in structural health monitoring, oil and gas industries, and medical devices due to their ability to provide distributed sensing over large areas. Applications: 1. Industrial automation. Electronic pressure measurement is integral in monitoring and controlling processes in industries like manufacturing, oil and gas, pharmaceuticals, and more. It ensures precise operation and safety by monitoring pressure variations in pipelines, machinery, and equipment. 2. Automotive. In vehicles, electronic pressure sensors are used for measuring tire pressure, engine oil pressure, and other critical parameters for ensuring optimal performance and safety. 3. Medical sector. In medical devices like blood pressure monitors, ventilators, and anesthesia machines, accurate pressure measurement is crucial for patient care. 4. Environmental monitoring. Used in weather forecasting, water management systems, and air quality monitoring to gather data for analysis and decision-making. Concluding, electronic pressure measurement, supported by diverse sensor technologies, underpins critical aspects of our modern world. Each sensor type, strain gauge, piezoelectric, capacitive, resonant, and fiber optic, offers unique advantages, enabling precise and reliable pressure measurements across industries ranging from aerospace to healthcare. If you have complex and specific scientific questions or engineering problems regarding the topics I have explained, you can contact me.